This is part 3 of high-throughput phenotypic screening using machine learning. This work is supported by Networks. The published papers and code can be downloaded from the link below. Information of quantitative optical phase and loss images are fused to extract multivariate biophysical features of each cell, which are fed into a fully connected neural network. The neural network maps input features by a chain of weighted sum and nonlinear activation functions into learned feature space, which is convenient for classification. This deep neural network is globally trained via area under curve, AUC, of the receiver operating characteristics, ROC. Each ROC curve corresponds to a set of weights for connections to an output node, generated by scanning the weight of the bias node. The training process maximizes AUC, pushing the ROC curve towards the upper left corner, which means improved sensitivity and specificity in classification. We use a k-fold cross-validation here by splitting data point into training, validation, and test subsets. In each iteration, one fold is used for fine-tuning the learning model, which is the validation dataset, and another fold is used for evaluation of the final results, which is the test dataset, while rest of the data points are used for training. The final reported results are aggregate of the outcomes from the test datasets. We show the result for classification of white blood cells and cancer cells by TSQPI label-free features. Training process of the neural network leads to improvement of classification accuracy over generations of genetic algorithm. In addition to the multivariate analysis using all 16 biophysical features extracted from TSQPI quantitative images, we also show training process by 3 single features. Red, green, and orange curves represent the best biophysical features in each category, respectively, namely morphology, optical phase, and optical loss. The values represent average balanced accuracy among training datasets at the end of optimization. Clearly, the final achievable accuracy by multivariate classification is considerably higher than that of single features. For each case, we show 5 receiver operating characteristic curves generated based on the test datasets. The gray diagonal lines show result of random guess classification. Multivariate analysis based on TSQPI images shows significant improvement in classification sensitivity and specificity. The fact that the classifier remained almost unchanged during the 5 iterations of cross-validation shows consistency and robustness of the classification. To visualize the multivariate classification results, data points are depicted in the space of the first 2 PCA components. To show the effect of the training dataset size in the performance of the learning model, the learning curves for training and test datasets of the tumor cell detection are analyzed. The tested learning curve shows that as the number of training data points increases, the test error reduces and the model performance improves. On the other hand, the training error contrastingly increases for a larger number of training examples because it's more difficult for the learning model to fit many training data points than a few. The discrepancy of the training and test errors is the generation error of the learning model. Comparison of the multiple machine learning classification techniques based on the biophysical feature extracted from the label-free cell images captured by TSQPI is shown below. Our area under curve based deep learning model, which is the first one, has both the highest accuracy and the consistency against the support vector machine with Gaussian kernel, logistic regression, native Bayesian, and conventional deep neural network trained by cross-entropy and backpropagation.